Hey everyone. So let's start looking at seasons. Let's go to the first slide here. So the reason for the seasons is the next thing we're going to study. And let's jump right in. Okay, so one of the big things that we're going to talk about is the sun's position throughout the year. And we're going to talk about this before we start talking about what the real answer for why do we have seasons is. Because I want you to understand that, of course, you probably already know this, but the sun doesn't stay in the same position. So if you look at its highest position throughout the year, it changes. So in winter, look down here, right? The sun is sort of low in the sky. That's the highest it gets, is not very high. And then the summer gets a lot higher. So how does that really do anything for us? Because this is the real reason for the seasons. And why does that even happen? Well, the fact that it reaches different heights during the year is due to the fact that the Earth is tilted. So this axial tilt of 23.5 degrees is very, very important. And remember, that tilt is relative to the plane of the Earth's orbit, which people call the ecliptic. Perhaps you remember that from the previous lecture. So we have this tilt, it's 23 degrees, 23.5 degrees, and that causes the change in the highest point between different parts of the year. So let's delve into that a little bit. So what causes the seasons? Well, it's really this tilt, and we're going to, again, explore that. So how much direct sunlight you get depends on the time of year. And we're going to look at that in a simulation in a second. And so the idea is that the Earth is tilted towards or away from the sun. So let's look over here in the northern hemisphere winter. And you can see that the northern hemisphere right here is tilted away from the sun. Okay, so that affects the directness of the light. It's less direct, and direct light causes more heating. Now, as we move through the year and we go here to what we call the spring equinox, we'll talk about those more in a second. Look over at the summer, you can see that it's very direct, and in these 2 points here, it's sort of in between those two things. Okay, so if you take a look at these little pictures here, in the winter you have the sort of indirect light, shadows are longer, and in the summer you have very direct light, shadows are shorter. And as we said, direct light causes more heating. So the more direct the light is, the more heat that the atmosphere is going to absorb, and the hotter it's going to be. Right, and this is the whole point. Is that it's the axis tilt that's causing the changes in the directness of the light. So let's take a look at a simulation and see if we can understand this a little better. Okay, so this is one of the University of Nebraska-Lincoln simulations. They're great for trying to understand all this stuff. So here we are, we have the Earth tilted, as we know, to the ecliptic. That's this plane going around the sun. Down here you can see the dates, right? So the 21st of December. And up here I've put the person at the North Pole. Let me bring him down to more like our latitude. Our latitude in Lynchburg, I know some of you are not actually in Lynchburg, is about 37. I went too far. Or didn't go far enough. You can't seem to type in this. It's a little tough to get him exactly where I want him. Let's keep it at 38. Okay, so he's at 38 now, roughly Lynchburg's latitude. And let's look what happens. So look down here, you can see sort of the local light directness. So if these arrows were straight down, then it would be 100% direct. And now here we come again, heading towards winter. Now we're in August. The light's getting less and less direct, you can see here. Right? Less and less direct as we're heading into winter. And we're going to get all the way to the winter solstice. And I think I'll stop the animation when we get to the winter solstice and take a look. Okay, coming up on it. Okay, something like that, close enough. And at this point in the year, notice the northern hemisphere, which is where our guy is, right, Lynchburg, is tilted away. And this is the point in the year where the Earth is maximally tilted away, which means the light is the most indirect during this time, right? Or during the winter solstice. So if we let it run further, we can see that the light is going to start getting more direct as we head into spring. Here we go. And right around here is, let me stop the animation because it doesn't want me to. Grab the earth. All right, grabbing the earth. Right around here is the spring equinox. And notice here, right, that if we look at the directness of the light, now it's still a little bit indirect, right? But it's kind of in between the two extremes that we see in the winter, at the winter solstice, and the summer solstice. We haven't got to the summer solstice yet. And notice that this sort of terminator, right, this is the line between light and dark, is perpendicular to the equator, which is right here. And that's typical of the equinoxes. So another word, a phrase that people use for this term is the vernal equinox, and we'll use that interchangeably with either the March equinox or the spring equinox. People use those terms interchangeably. So let's pull the earth around, come on earth, come, to the summer solstice, right? So this is the summer solstice around June 21st. There we go. And notice this is the time, the light is very, very direct. And as I move forward in the year, right, it starts to get less direct. It's kind of hard to move this animation. Here we go. Now it's getting less direct, till it's right between the 2 points. Notice that the arrows here are angled with respect to the ground, because this person is at 37 or 38 latitude. So if I pull him down to the equator, notice now the direct light is straight up and down, right? Now if we notice on the equator, what happens? The directness of the light changes. Oops, move over. This animation really doesn't like me. Okay. How if we just let it run? Okay. So now we're roughly at the equator. And notice that the change between direct and indirect is not by much, right? So it doesn't change very much on the equator. But if we go put our guy back up to Lynchburg's latitude, it does change quite a bit. So as we see, the directness of the light really changes through the year, and it's all because you're either tilting towards the sun or away from the sun. So, as we see, the axis tilt is responsible for this change in directness in light. Now, so what about distance? And, some of you may be thinking that distance must play a role, right? Don't we get closer to the sun and farther away? Well, it's true, we do get closer to the sun and farther away throughout the year, but it's not by much. And even if you think that the change between here, so here, let's look over here, around January 3rd, we're at the closest we are to the sun, and over here in July, we're the farthest away. So even if you think, a couple million kilometers is a big difference, it doesn't seem to be in the right time of year, right? So we're closest to the sun in winter, right? And farthest away in summer. So that really doesn't fit with it being the variation in our distance from the sun that causes the seasons, because of course, during winter is when it's coldest, and in summer is when it's hottest. And that just doesn't fit with this data. So it's really the tilt that's making all the difference. Now we talked about directness of the light, and we're going to talk about another way that the tilt causes the seasonal change. But let's just take a look at this misconception that the seasons are caused by getting closer or farther away. It is ubiquitous, this misconception, and I urge you guys to go out and ask your friends what causes the seasons and see what they say. So let's take a look at a video just to point out this misconception. And this is Harvard University commencement.
Lee Fingerman, candidate in art.
Despite a lifetime of the very best education, students in our classrooms are failing to learn science. Many of these students will graduate from college with the same scientific misconceptions that they had on entering grade school. To test how a lifetime of education affects our understanding of science, we asked these recent graduates some simple questions in astronomy. Consider, for example, that the causes of the seasons is a topic taught in every standard curriculum.
Okay, I think the seasons happen because as the Earth travels around the sun, it gets nearer to the sun, which produces warmer weather, and gets farther away, which produces colder weather, and hence the seasons.
How hot it is or how cold it is at any given time of the year has to do with the closeness of the Earth to the sun during the seasonal periods.
The Earth goes around the sun, and it gets hotter when we get closer to the sun, and it gets colder when we get farther away from the sun.
These graduates, like many of us, think of the Earth's orbit as a highly exaggerated ellipse. Even though the Earth's orbit is very nearly circular, with distance producing virtually no effect on the seasons, we carry with us the strong, incorrect belief that changing distance is responsible for the seasons.
Yep. So even at Harvard, right? So I think it would be fun for you just to ask everybody you know how the seasons come about, and see what they say, and hopefully you can correct them and contribute to people actually understanding the science of this a little better. Okay, so now we know distance really doesn't play a role, and you can, when you're talking to people about this, you can point out that we're actually closest to the sun in winter, and they can go look that up and verify that. And remember, right, the tilt causes the sun's position in summer to be at higher altitude and in winter to be at lower altitude, which of course we know does affect the directness of the light. However, there's another effect from that contributes, and I just put this in here so you can have a visual picture for all the different points in the year. The spring equinox, the fall equinox. By the way, this is the vernal. People, like we said, this is the vernal, and this is the autumnal equinox. So nice words here. The winter solstice and the summer solstice, and I'm not sure why that's not over here, but this is the summer solstice. Okay, so the other effect that's caused by the height of the sun is the length of the day. So think about it, right? When in summer, the day is very long, right? And in winter, it's short. So the winter solstice is actually the shortest day of the year. So after the winter solstice, days start getting long again until the summer solstice, and that's the longest day of the year, and then start getting short again. And look at from this little picture here, you can see in the winter, right? Here's the path of this. Oh, the other way. Here's the path of the sun going up, coming back down, right? So it rises, gets to its highest point in the sky, which isn't very high, depending on your latitude, and then sets again. And it's not up for very long, right? This is the reason that the days are short, is that you're tilted away from the sun, and that means that it doesn't get very high, and so it does not stay up very long. And contrast that with the summer solstice. Here's the rise, stays up for a long, gets really high in the sky, stays up for a long time, and spends a lot of time up. And that means there's more opportunity for heating. And that's why it's hotter. So that's one of the reasons, right? So the directness of the light and the length of the day are the two big things that are caused by the tilt. Okay, so let's actually look at a simulator for that. Oh, and I actually want to show you this first, then I'll show you the daylight simulator. So this is another one of those University of Nebraska-Lincoln simulations. And this is cool because what they did is they took a picture every day from the same place throughout the year. And right now you can see we're starting into summer here, right? So, and these little dots here, which are hard to see, but sometimes they couldn't take a picture for some reason. And so there's actually the dots are when they couldn't take a picture, see? So for some reason they just couldn't take a picture that day, or maybe it was raining or snowing or whatever it was, right? Or in this case, raining because it's spring. And they couldn't really take the picture. So there's some times where they have these big gaps in the data, right? But they did take a picture, tried to take a picture every day throughout the year. And over here is plotted the height of the sun. And you can also tell that by the length of the shadow of this building. Let's start it over here at the beginning of the year. Here, let's move over. Here we go. And I'm just going to let it play. So here we are, the end of August. Look at that shadow. It's pretty big, right? And let's start. Oh, sorry. That was end of December, not end of August. Right. So here's a really short shadow. I'm going to pause. So if we go back to the summer solstice, that's the shortest shadow you're going to get, right? Look at the little guy's shadow back here, because the sun is the highest it's going to get. Right here at roughly the summer solstice. Move over a little bit, get the summer solstice for real. June 21st, there we go. Okay, that's the shortest shadow. The sun is at its highest point. And now if we run, we'll see the shadow start to get longer as the sun doesn't rise quite as much. So what they're plotting here is the highest point that it gets, right? All right, every day. All right, so let's try this. Here, look at that shadow get long. Yep, you're going to see some snow in a minute. There it is. Oh, lots of snow. Okay, now we're going back. Short shadow, summer solstice. Coming up on the longest possible shadow right around here. Let's go back to the winter solstice. Right? There we go. That's the longest shadow. Look how low that sun is. And Nebraska is a few degrees more north than we are. So, in Lynchburg, we're about 37. They're at 40. So their sun is not going to get quite as high as ours in the winter. Okay. Let's start the animation to look at one more time. Snow, snow. Spring. Trees, the leaves come back on the trees. That's my favorite part. I'll watch that one more time. Let's see. Oh, fall. Did you see fall? Let's go back. Go back. Go back. I want to see fall again. So look at the trees. They're super green, 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 green. And they start to get beautiful colors, like there. And then they lose their leaves. Someone sweeps them up, apparently. And now, no leaves on the trees. Shadow's super long, getting snow. And then our leaves are going to come back. There they are. Anyway, so I love this because you can really see these changes in the shadow and the height of the sun. And let's look at the daylight hours. Oops, I didn't want to go that high in latitude. Let's go to Lynchburg again. Come on, Lynchburg, where are you? There we go. All right, so that's roughly the latitude of Lynchburg. And this over here is plotting how long the day is. So right now, let's go to the to today's date. Let's see, what is today's date? It's the 19th of May. Although I'll be watching this at a different time, but you can play with the simulation too. So right now, there's about 14 hours of daylight here in Lynchburg. And that means there's about 10 hours of night. And as we head towards the summer solstice, so let's head over, here we go, to the 21st. Notice that's the longest day, and I'm going to start getting shorter days as I go down here, right? The longest day, about 14.5 hours, which is, it's a good long day. And let's head in. The day's going to start getting shorter, 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 until we get to the autumnal equinox. Remember, that's the fall equinox, the September equinox. It's kind of hard to see exactly where it is. There we go. Well, yeah. And that's when you have exactly 12 hours. 12 hours day, 12 hours night. Right? So let's keep going. Let's go to the winter solstice. where we have, ooh, it's pretty short day, 9.5 hours. And you're all familiar with that, right? When it gets dark really early. And then if we head over again to the vernal equinox, remember that's the spring equinox, we're going to hit 12 again, right here, sort of flipped over. So the length of the day changes, and you get more daylight in the summer, which means the sun's up more and can heat more. And this is all due to the tilt, right? As we saw in that little figure we saw in the PowerPoint. Okay, let's, just for fun, let's take this up super high. Oh, what's going on over here? Look at this. So now we're really high up in latitude. Look at this. And their longest day is super long. 21 hours of daylight. Imagine that, right? And even worse, right? 21 hours of night, right? A 3-hour day. Wouldn't that be great? Not really. So let's go even more north and see what happens. Oh boy, something's going wrong here, that's for sure. So let's see. Here we are, 80, almost at the almost at the North Pole, which would be 90 degrees latitude. And look what's happening. Let's go back here. Okay, so right now, here's the vernal equinox. Fine, 12 hours a day, 12 hours a night, we're good. But now as we move forward in time, look what's happening, right? Move forward in time. The amount of daylight is growing. Of course, it's always going to grow. If we're moving towards the summer solstice, the amount of daylight definitely grows, but not this fast, certainly not where I am. Look how fast it's growing, and it gets to 24, and you have daylight all day long. All day. And then, right around here, we start to drop like crazy, right? Now we're down to 9 hours of daylight. And right around here is the autumnal, right? You can tell the autumnal equinox is when you have 12 hours a day, 12 hours a night. And you can see that's right here. But we're still falling, heading into winter. And now we have night all the time. No daylight whatsoever. Night, 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 night. Until, right around the end of February, beginning of March. And we start to get a little daylight again. And we hit the vernal equinox again at 12. And start heading into the 24-hour days. So this is quite extreme, as you can imagine. So here's the path of the sun on the summer solstice in the Arctic Circle, which is where we were, basically. And the summer solstice, remember, day all the time. Now the sun moves, right? It gets a little higher, a little lower, but it never sets. So you get a little twilight going, but you don't get any night during that time, as we saw. Okay, so here's the season summary. So the axis tilt is the reason for the seasons. The axis tilt causes the directness of the light to change and causes the length of the day to change. And those two things combined are what changes the temperature, right? Now, you might be thinking also, you probably know that there's differences. Even at the same latitude, there's differences. So, for instance, Lynchburg's latitude is about 37, and San Francisco's latitude is about 37, a little bit more. And you may or may not know, but San Francisco really doesn't have any seasons. It's kind of like 65, 70 degrees all the time. Of course, it gets colder at night, but it doesn't really have the same kind of variation that Lynchburg, Virginia has. It never snows there, like never. And so it's very different. And these kind of changes are not because San Francisco's on the west, are not because it has a different longitude, right? Because that really doesn't play any role in what kind of seasons we experience. But it's more about local things like ocean currents and things like that. So the reason that San Francisco has different weather than we do here in Lynchburg really doesn't have anything to do with the fact that it's far away from here, right? Because we're roughly at the same latitude. It has to do with a lot of other factors. So, given that we know that the axis tilt is what causes the seasons to change, what do you think about Jupiter? Jupiter has like a 3-degree axis tilt. Do you think there's much seasonal temperature variation on Jupiter from the seasons, right, as it goes around the sun? Well, in fact, no. Jupiter's axial tilt is very small. There's not much variation in the directness of light or the length of the day, so you wouldn't expect there to be giant variations in, seasonal changes in that temperature. Okay, so now it's time for you to answer a question. So here's a question. Remember, you got to pause the video so that it doesn't disappear on you. And then choose your best answer from the list below.